Previously, I introduced photons and the photoelectric effect, and the key concepts we encountered were that light is transmitted in packets of energy, which are particles called photons. Each photon has an energy equal to the frequency of the light times Planck's constant. We will now look at the photoelectric effect more quantitatively. We saw that if the energy of an incoming photon was too small, an electron bound to a proton would not be able to absorb any of the photon's energy, since it is not enough to bring the electron to the next allowed state, the delocalized state. To expand the model, I propose to you that in a solid, an electron doesn't have the choice between existing between two energy levels, but has the choice of existing between two bands of energy. One band corresponds to being bound tightly to the atom, called the valence band, which has a maximum energy of eV. The other band corresponds to being a free electron, and is called the conduction band, which has a minimum energy of EC. This no-go zone in between still exists, and jumping from one band to the other requires an energy of at least phi. So any incident light with photon energy less than phi will fail to create any free conduction electrons. So with photon energy that is too small, we don't measure free electrons. Now we increase the frequency of the light we shine onto the metal, and eventually we reach a point where all of a sudden we do start measuring the presence of free electrons. This is because the photon energy is now sufficient for the electron to jump from the valence to the conduction bands. The frequency at which this occurs is called the cutoff frequency. All photons with a higher frequency than this will be absorbed by valence electrons that enter the conduction band. The minimum energy a photon can have in order to promote an electron to the conduction band is called the work function, and it is equal to what we have been calling phi. Each metal will have its own work function. We relate the cutoff frequency and the work function here, simply stating that the minimum energy of an incoming photon must be the minimum size of the required jump to create conduction electrons. Let's imagine that a photon with more energy than the work function hits the metal. We know that the photon must pass on all of its energy, and so the electron gains more than it needs to enter the conduction band. What happens to this extra energy that it acquires? It is kept in the form of kinetic energy. The electron will move faster if it has more leftover energy. If we set up an experiment so that the conduction electrons are made to fly off of the metal so we can measure their speed, we can test this. By conservation of energy, the energy of the incoming photon, HF, must be equal to the jump that the electron makes to go from the valence to the conduction bands, plus however much kinetic energy it has left over. To make this equation more general, we instead choose to write it in terms of the work function and the maximum kinetic energy. The work function is the minimum amount of energy it takes an electron to go over the no-go zone. So we have to make the kinetic energy term the maximum leftover energy an electron could have. For example, if a metal had a work function of 2 joules, and we shone light which had photon energy of 3 joules, the maximum kinetic energy we would expect to measure in conduction electrons would be 1 joule. In semiconductors, the energy gap between the valence and the conduction bands is very small. So small, in fact, that by increasing the temperature, the electrons might gain enough heat energy in one go to jump across the gap and become conduction electrons. This means that the resistance of a semiconductor circuit decreases when the temperature increases, since more free electrons can carry a current. This is not the same in metals, where the gap is big enough that unless you reach extremely high temperatures, increasing the temperature of the metal will not promote electrons, but will instead just make the atoms in the metal vibrate more. Conduction electrons then hit these atoms more, and they slow down, which means an increase in resistance. An LDR, or a light-dependent resistor, relies on incoming photons to excite valence electrons and promote them to be conduction electrons. the photon energy must be sufficient to jump the gap. And then if we increase the number of photons, in other words, we make the light brighter, we will get more conduction electrons, and so the resistance will decrease.